Hello everyone, in this video we will learn high-level synthesis optimization in terms of area and performance. We will be doing the optimization for the bubble sort algorithm. In this algorithm we will gonna insert the pragmas. What is pragma? Pragma is a compiler instruction or derivative that tells the synthesis to how to optimize or modify the hardware implementation without changing the C code's functional behavior. It is like giving ints or orders to the compiler. So in this I have given the first pragma as a RAM cyber array. This is how you have to define the pragma. Then I have again given pragmas for over here in the inside the loop unroll times uh, unroll times and unroll times all. This is a forward pass bubble sort algorithm. Let's analyze this and synthesize, and let's see what are the benefits of using pragma and how we can optimize it. Now it's done. Now let's synthesize it. As you can see, we had inserted a pragma called RAM, and you can observe the resource utilization. It has using ALUTs 353, registers 93, and block memory bits of 64, and there is no DSP blocks. Why it is using block memory bits? Because we are inserting RAM as a pragma, and it is also using a memory which is write and read memory, which is 8 bit and 8-bit word. This is a functional unit. It uses only one functional unit, and latency is of 72. Latency is of 72 cycles. And it uses total 72 states. The critical path delay is 8.622 nanoseconds, and we can always observe the data path. This is how the data path looks like. Since the latency is 72, we can conclude that the performance is very slow, since it is of the latency is 72 and delay is of 8.62 to 88 nanoseconds. Now let's change the pragma to register over here. And let's try to unroll times. Let's try to make the inner loop unroll times as 0. Let's tell the tool like not to do any unroll times. Let's save this, then again analyze, synthesize it. So this is our second design. What we did, we changed the RAM pragma to the registers, and we also changed the unroll. We mentioned not to unroll time, so it is 0. Now you can all see that it has very less, it's consuming very less LUTs and very less registers with a memory block of 64, but it has a latency of 72 and delay of 6 point and critical path delay of 6.1408 nanoseconds and latency of 72. So from this data we can always conclude that the performance is very high, but the area is very the area consumption is very low. And over here we could see the data path. Now let's again change the design. Let's again change the pragmas. Let's give both unroll times all. This is the pragma what we change over here. We had mentioned as cyber unload times all and registers, and we could see the report that it's consuming 733 lookup tables and 90 registers, but the latency the performance is very good, but it is occupying more area, and it is using only 16 sets, and it has a critical path delay of 20.05 to 8 nanoseconds, and it is using no memory and only one functional unit. Overall, we can say that the performance is really good since it is only 16 latencies, because the latency is very low and the area is also very utilized much. This is how the data path looks like. So the so we have found a different three we have got three different designs, and we can conclude that the tool is optimizing really well, but each design adds its own area and performance trade-offs, and we can always change these pragmas, and we can always generate a new circuits, and this is how we'll use to optimize the tools. Thank you.